Welcome to today's webinar with the title Mille feuille for the anniversary basic physical PCB sample WE.fan. I am Andreas Schilpp, your host and speaker of today's Würth Elektronik circuit board technology webinar, and I would like to welcome you. And now I wish you lots of fun and new information. So this is the agenda for today's webinar. First, we will care for the wordings basic and standard and what's the difference between that two words. Then we will have a closer look at base materials which are used in producing printed circuit boards. Then we will have a closer look at the steps of a production of a multilayer, step by step. Then we will have a look at the physical PCB sample for the basic technology which is called WE.fan. And last but not least, we will answer the top 3 questions from our 100 webinars in detail. So that's it for today. And by the way, going back to the slide, this is our 100th webinar. So we had 100 German webinars, and this is the number 100 in English language. So in total we have got 200 webinars already. And yes, I'm still curious in the technology and in talking to you and answering questions. So I like to find solutions anyway. So let's start with the specifications or with the meanings of basic and standard. And the standard is a category or a classification. And for PCBs, that means standard is available from all plants at a favorable standard price. And that could be any technology. It could as well a rigid flex technology or HDI technology, embedding technology. There are all standards everywhere. Other classifications or categories are advanced or maybe even state-of-the-art or leading edge. So, for example, here we can see design rules. One category is technical standard, which means standard at least, and the other classification is advanced requirements. So that, by the way, it's an excerpt out of our Slim Flex design rules. So standard and advanced is available in all technologies, more or less. We can compare this maybe with the car. So you can buy a car in a standard equipment or version. You can also buy an advanced or avant-garde, maybe is or was called at Mercedes in the past. Or you can buy a sports car with additional equipment and power and things like that. So that's more or less than an advanced solution or an advanced car, but you can also stay with the standard. So that's the category or classification. So another example for standard is that we provide standard stack-ups. That means we are using standard materials which we have in stock. We have standardized processes which guarantee smart processes with a high quality and at a favorable price. So that's standard in general. So coming to basic, that's now a technology, and by basic we mean single-sided PCBs, double-sided and multi-layer printed circuit boards. So that's what we are caring for today. So again, the 3 different types in basic technology. It's a single-sided PCB, it's a double-sided PCB with plated through holes, as you can see here in the middle of the slide, and on the right side you can see multi-layer with 4 copper layers with plated through holes again. So that's what basic technology covers. So this is the next step of our agenda, having a closer look at the used base materials in a multi-layer. So of course we are using prepregs. This is an artificial wording which comes from pre-impregnated. That means that's glass cloth impregnated with resin, and the resin is not fully cured, but it's just partially cured. So it's pre-impregnated, it's not fully cured, so it still has the ability to glue things together under pressure and high temperature. On the other hand, we have copper foils, of course, and the combination of prepregs and copper foils could be an inner layer core, which we see on the right bottom side. You can find even more details on base materials in our webinar we did last year, Basics of Printed Circuit Boards Production Part 1. You will find that on YouTube or on our YouTube channel or on our website at the basic page. Okay, so now let's have a closer look at the production steps, step by step, producing a multilayer, and we are starting with a base material, in this case a inner layer core. So we just see from the top or from the bottom, we just see copper, but inside there is the dielectric material already. And the first thing we are doing in production is of course cleaning, which is not shown here, then the next major step is the covering with a photoresist and the imaging process. So now we already can see the artwork. We also can see the overlay filling the area outside the artwork to achieve a well-balanced copper design for the whole panel. We also see registration, fiducials, and some small writings, legends, and so on. So this is after the imaging of the photoresist, and you can see brighter blue, yes, it's more orange, which is the area which was not imaged, and you can see the more or less dark blue or gray blue areas. The photoresist there has seen light, UV light or laser light, and thus curing, and so that's the dark area and the polymerized photoresist. And the next step is removing this not exposed resist. So what we can see here is photoresist staying on the copper and protecting the copper during the next step, which is etching. So etching the copper, we can see here after the etching process, exposing the base material inside of the core. So resist stripping already performed on the sample on the left side, and after that process we need a quality control ensuring the quality of the process itself and the adhesion promotion, which results in a darker color of the surface, providing a rough surface, improving the adhesion in the following lamination process to produce a multilayer out of one or several cores and prepreg and copper foil. So that's the next step we can see here. So here we are producing a 4-layer in the graph. So we have the formerly produced inner layer core. Then we are adding copper foil on the table and prepreg on top, then the core, another sheet of prepreg or more sheets of prepregs, and another copper foil. After lamination process, it looks like that. But to be honest, it looks, in reality, it looks like this. So this is the multilayer inside, and we have some additional copper area which has to be cut, and prior to the cutting there is a process called X-ray drilling. So we are looking inside the panel, finding the inner layer fiducial marks, and then drilling a new registration hole for the following processes. So after the edge cutting, we now have a very clean edge of the board, also radius at the edges. So that's perfect for the following steps which are performed. And the next step is drilling, mechanical drilling to be accurate. And this is done by a drilling machine, of course. We can see different tool diameters here on the example. And after the mechanical drilling, there is a direct plating which makes a very thin copper layer inside the hole. So the barrel is covered with thin copper already, and the following electropanel plating process adds even more copper on the surface as well into the barrel, which was drilled by the drilling process. So perhaps we can see the difference on the pictures here. So here we can see a rough hole inside a whole wall or barrel which is rough without copper, and here we can imagine there is already copper plated to the wall of the drill hole. Okay, so next step, again we need photo imaging process, but this time inverse to the inner layer process. So this time we apply photoresist to the whole surface, but the imaging is different to the inner layer. So this time, after the imaging and the developing of the photoresist, we can see the copper of the artwork, which will stay finally. So the exposed copper will be plated, thus adding more copper to these regions, and as well to the barrels, to the drill holes, of course. So we will see in the next step there's additional copper here in this area and this area. Of course, here in the area where we have the imaged photoresist, the cured photoresist, there will be no more copper plating in this region. So finally we got more copper here in the exposed areas as well, in the barrel here, in the drill holes, and finally ending up in a tin resist, which is also plated on top, which looks gray, and which protects the copper plated there, and protects it in the following alkaline etching process. So it's how it looks after the removal of the photoresist. I go back one step, so this is with photoresist, and finally after removing or stripping the photoresist, we can now see the base copper which was there from the early beginning when we laminated the copper foil on the multilayer. So this is the base material, the base copper to be correct, and this has to be removed to finally make the lines and spaces, the isolations and the copper tracks working. And here we go. After the alkaline etching process, we now can see the FR4 material from the pre-preg and even from the cores if there's no copper on it. So that's the yellow color which comes from the base material. So there's still the tin edge resist on the copper, and this has of course to be removed. So after tin stripping it looks like this. We can see the final artwork in pure copper. After the cleaning process, we have a coating with solder resist, completely, in this case, fully a coating of solder resist. Next step is the imaging and development of the solder resist. So now we can see copper again, and this copper is not capable to be soldered, of course, so it's oxidized copper, so it has to be cleaned. But prior to the cleaning, there are other processes like legend print as an option, and then final curing of the solder mask with the legend print on it already. And after this process, the copper is even more oxidized, so it has to be cleaned again. And then it's shiny, bright copper color, but still copper. And then we will applicate the surface finish, which is Enig in this case as a surface finish. So now it's nickel and gold on it, and afterwards there's an option of maybe a peelable mask. Then we have to separate it, milling or regrooving, washing, electrical testing, final inspection and documentation, packing, and finally shipping of your boards. So this is a production of a multilayer step by step. And now coming to the physical PCB sample, WE.fan in detail. So we have three different parts of the sample. You can see here, this is, as you know it from your parts, from your PCBs, this is a multilayer fully laminated with all the materials and as well with the legend print and with solder mask, of course, and surface finish. Then we have a second part. There are also all the materials on it, but it's not laminated. You can see this is a fan already starting here at this point. And in the third section, we even miss the outer layers. We still have the two cores, the inner layer cores and the pre-preg in between, which has no copper on it. So the production is done like a rigid flex board. I switch on my camera to show it to you. So this is the physical PCB sample prior to the separation. So you can see there is a separation foil inside which prevents the material from the gluing. So the white material is the separation foil. It sticks a little bit to the material, so it's hard to remove. But I can show it with this outer layer, so you can easily detach it and have the fan as wished. So using our rigid flex technology allows us to do it in an easy way. So you may order the sample if you haven't done it yet by using the QR code or the short link here. So there is a description of the sample as well as the ordering form. You can order your personal PCB sample. So here are the characteristics of the sample, and we just switch to the internet and see the description there. So you should now see our internet presentation, basic physical PCB sample WE.fan, and some introduction to the sample, and then the characteristics and overview. Let's go through the points. So first of all, we can see the stack up. This is a 6-layer multilayer in a standard stack up. The darker gray areas showing us the cores. So we have 2 cores. The brighter gray meaning pre-preg in between the 2 cores, and outside facing the outside copper on top and on bottom. So it's called basic 6 for 6 layers, multi-layer 6, 1.62 millimeter thick, and with 1 ounce copper on the inner layers, starting copper. So the fans you can see here from the side again. I already explained this. The contour is milled. As usually we can see the glass fibers inside, but it's a precise outline here done by a milling process. We also have plugged wires, but there's a small difference to the specification done by the IPC 4761. So in our case, we already had the ENIC functional surface prior to the plugging process. So that means we have also ENIC inside the barrel, protecting from corrosion, so for achieving a high reliability. Regarding the structures, this is standard, 6 mil line space. We have a peelable mask. The idea was to remove it from this finger here on the right side, tapping that and slightly drawing and removing it from the plated through holes. On the bottom side we have something kind of special option, which is an isolation foil that's made out of polyimide. It's the same material we are using in rigid flex technology. It's cover lay or combination out of polyimide and gluing film. The contour, the outline is milled and then glued under vacuum to the surface. So this has a high breakthrough isolation, high breakthrough voltage, excellent isolation, and could be used to protect the PCB from contacts to the housing maybe, or heatsink. So regarding the components, the component with the highest density is a BGA with a pitch of 0.8 millimeters, and for BGA pitches less than 0.8 millimeters, we generally recommend HDI design using micro wires. Another option is the usage of a data matrix code, also having the possibility to have a dynamic content. And last but not least, there's a QR code on the sample, and the content of this QR code is the short link to this description, exactly this description. So if you lose your paper coming with the sample from us, you every time have the chance to find the description again. So just go on the QR code and you will find the description here on our internet presentation. Okay, so going back to my PowerPoint presentation, here we are. So we not just have the basic physical PCB sample, we also have some different ones covering rigid flex covering slim flex, covering stretch flex, or HDI technology, embedding technology, printed polymer technology, and last but not least, high-speed technology. So feel free to order your personal physical PCB sample free of charge here. So you can use the short link for this overview and then finding your sample you want to order. So the last point of the agenda is the answering of the top 3 of the questions out of 100 webinars. And this is one of the top 3. Question is, what influence does the number of holes of hole diameters in a design have on the price of the PCB? And there's an information to understand the answer. Drilling machines for volume production have a revolving tool chain with several thousand carbide tools. So that's important to know and to understand the answer. And the answer, of course, is the number of drilling diameters has a very small influence on the PCB price, as the machine has an incredible number of tools in the machine, and the changes are done automatically even after the defined tool life has expired. So in contrast to this, the following parameters have an influence on the cost, which means drilling diameter and number of drill holes, of course. So some more information about this. Here we can see 3 different drilling diameters. You can see the numbers on the slide. And what's also important to see that, of course, the length of the drilling tool is reduced by reducing the diameter. So that's important regarding the stability and the ability to drill through thicker stacks. We will see that in a second. So here we have a panel stacking for this mechanical drilling. We are drilling into FR4.1 cores. That means advanced FR4 material with a TG of typically 150 degrees C and filled to reduce the Z-axis expansion, which makes the material more reliable, especially under thermal aspects, thermal changes. So that's a more robust material. Thickness 1.6 millimeter, and we can see now if we use a drill bit with 0.55 millimeter diameter, we can drill through a stack of 3, reducing to 0.35. The stack just has 2 cores and 0.25 millimeter. We can just drill 1 panel at a time. That means, as a consequence, that on the other hand, the tool life is reduced, the thinner the drill bit becomes, and also the panel stacking, as already discussed. So in a consequence, the time to drill 15,000 vias, it takes us 12 minutes for the large tool, for the middle tool 24 minutes, and finally 48 minutes for the small tool. And we need different numbers of drill bits to doing this, as the tool life is different. So for the big tool, we need 4 drill bits for 15,000 wires. For the middle tool, we need 7.5, so 8 drill bits, and 30 drill bits for the small 0.25 millimeter drill bit. So as a price indicator for the drilling process only, that means if we assume 100% for the large bit, we double the price for the 0.35 millimeter bit, and even have a factor of 4.6 for the small bit. So that's quite a impressive difference. Different kind of view on the process and the cost. We have, of course, a fixed cost for the mechanical drilling, preparing the machine and loading software and things like that, which is done automatically, by the way. And adding to this the variable costs for the mechanical drilling, and depending on the drilling diameter, this is linear rising up. And here we have some more details on the drilling frequency. For a drill tool of 0.2 millimeter, we have 3 drillings per second, and 1/10 of a millimeter more enables us to have already 8 drillings per second, which is pretty fast. Next question. Separation of a panel. What does the choice of separation technology depend on, and what are the advantages? So below the question we can see different kinds of separation. We have scoring lines or V-grooving lines, we have milled slots, and on the right side we have a completely milled delivery panel without any scoring lines. So regarding the question about the choice of the separation technology, that depends on the design, of course. Milling can realize complex contours. V-scoring or notch milling only can cut straight lines. And of course, for highly complex outlines or high demands on contour quality, we always use milling technology. But milling is always more expensive than V-scoring regarding the process itself, and we will see some more effects on the price afterwards in a minute. On the other hand, cutting of a scored panel requires appropriate tools and puts a strain on the material and possibly on components which are located very near to the outline. So care for that, especially if, with ceramic components. Punching or sawing is also used for high volume production, but needs special equipment, of course. Laser cutting, on the other hand, is very flexible, but due to the point that you have to cut through the complete material to separate that, it's mostly used for very thin panels, especially for flex panels. Okay, so some more information about panelization. As we have already seen with our PCB sample, I just show that it's a very small panel, but showing all the registration holes and the frame around we need as a manufacturer. That's what you cannot use for your design. So it's the outside border which we need for our registration especially. So if we route this kind of design, we have 3 in a panel, and using V-scoring we ending up in a 4 times design in that panel. So that could make a difference, and if you could change to V-scoring, that makes a price advantage, of course. So in this example, it's a 33% difference. If we are looking for a delivery array, this is an example done by routing, and the alternative using V-scoring is this, without any distance in between the single PCBs, so in this rectangular shape that's possible. So the difference is 85 PCBs on a panel compared to 56, so that's a huge difference in some cases. Another thing is delivery array in routing. and routing and compared to V-scoring without the distance in between. So that could also do a huge difference, in this case even 100%. So another calculation showing us the difference between the V-scoring delivery array in this case, which is, to be honest, a special but very impressive example. So it's a small PCB, 20 by 40 millimeters, and in this case we have 216 PCBs on the production panel. Changing to milling would mean 160 with 5 millimeters separation channel, and if you need more separation channel, maybe due to connectors overlapping the outline, maybe, so changing from 5 millimeter distance to 10 millimeter distance, reducing to 128. So that's quite a huge impact on the price finally. So some more information about influence on the price. So here we have a more or less standard routing contour, which means we have 4 changes in direction during the milling process, and we are using a routing tool 2.4 millimeter, which is absolutely standard tool. Compared to this really complex milling contour, here we need around about 30 changes in direction and a high routing time, and the need of a smaller tool with 1.8 millimeters. So difficult outlines and shapes have a huge impact on the price for the milling process finally. So last question out of the top 3 of the 100 PCB webinars in the aspect of basic technology is that how does the stack up influence the price of the PCB? So we again see a standard stack up for a 6-layer basic multilayer, and the answer is the influence on the price of a PCB due to the stack up is due to the type of material used, and which is cores or prepregs, or maybe even the need of additional blind cores to fit the thickness requirements. And on the other hand, by the quantity of materials used and due to the necessary processes to reach this stack up. So we will see some examples in a minute. So due to the processes means maybe multiple exposure processes or especially multiple pressing processes, lamination processes, and metallization processes, maybe for HDI microwires. So let's have a look at different thicknesses of multilayers. All of them have 4 copper layers. This is more or less standard 1.6 millimeter, then a thicker one, a slightly thinner one with 1 millimeter thickness, and half of that 0.5 millimeter width, which is quite thin. So the difference is in the usage of the material, assuming that we have a price indicator of 100% for the 1.6 millimeter board, we see that we need even more material for the thicker board. In this 2.4 millimeter cores, you can imagine that producing this core needs a lot of more prepregs to get this thickness, so that's more expensive. Reducing the thickness helps to reduce the cost slightly, so this core is just 0.41 millimeter thick, And reducing even more in thickness means that we have to handle a very thin core with just a tenth of a millimeter, and this has an impact on the yield, thus resulting in a slightly higher price. So another approach to understand the question or to answer the question, which impact on the price we have based on the stack up used. So here we can see a standard stack up with 2 cores, as we already learned in the production step by step. 2 cores here in the dark gray, prepreg in between, and prepreg as well facing the copper foil on top and on bottom. So we have 2 cores and we have 6 prepreg layers. So if there is the requirement to use thinner cores due to signal integrity, maybe, we can see that we have the need of a lot of additional prepregs, which ends up in a higher price, of course. So price indicator for the standard stack up is 100%, and for the specific stack up, due to the need of more prepregs and the handling of the thinner inner layer cores, results in a price indicator of 116%. Additional costs, as already mentioned, for the handling of the thin laminates and for the additional prepregs in the stack up. So now let's have another look on the possibilities of doing a stack up. Here we have a standard stack up, as we call it, in foil lamination. Foil lamination means that we are ending with a foil outside prepreg foil, and the cores in between. If you want to have a core-based stack up, that means we are using cores outside, cores symmetrically inside, and another outside core on the bottom side, and in between we have prepregs. So the difference here is that we need additional material. So we have 3 cores now, and we need multiple exposures for the outer layer cores. So we have to image and also etch the layer 2 and the layer 5 prior to the lamination process. And again, we have to laminate the final multi-layer stack up again. So these are additional processes we have to perform. And it's comparable to an 8-layer PCB finally. And maybe for special stack ups, we need filling cores without copper on it to meet the thickness requirements. If we have very thin cores and need final thickness of 2.4 or 3.2 millimeters finally. Okay, these were the top 3 questions out of the 100 webinars. Now let's come to the summary. We have learned that basic is a technology and standard is a category or classification, which we can find in each technology. So please be aware of using the right terms in the future. The basic physical PCB sample WE.fan shows many technological basics and some options, and even more physical PCB samples of other technologies as shown are available from Würth Elektronik. Further information on basic technology on our website. Use this short link /basic to find these information, which are basic design rules, basic technology poster, FAQ section, and finally the basic standard stack ups. So thank you very much for joining us today. Thanks you for your patience over the years and for your ideas for new topics and webinars. So thank you very much and good luck for your projects. Stay healthy and yeah, goodbye for today.